Hey, my name is Aaron Balke, and in today's video I'm going to be breaking down my logistic regression modeling assessment for my data analytics masters. This assessment uses a theoretical hospital dataset with patient demographic information, patient health information, and this presentation was made originally for that assessment, so there may be some assessment-specific information in here. Just be aware of that as you are watching it. I hope you enjoy. Hello, my name is Aaron Balke, and today we're going to be breaking down my D208 Task 2 Logistic Regression Modeling Performance Assessment. For this performance assessment, our question is, does high blood pressure correlate to any other specific conditions or any other specific features in our data set? And using this logistic regression model, we'll be able to predict cardiovascular requirements for our patients. We'll be able to figure out, based on other information, is this person more likely to have high blood pressure and in turn have cardiovascular problems related to high blood pressure. So it'll allow us to effectively treat patients and give them the ability, we can warn patients that they're highly susceptible to cardiovascular problems. So that's the goal of our analysis. For logistic regression modeling, some assumptions will be, first off, that we have a binary dependent variable. For logistic regression, our dependent variable is going to have to be a 0 or a 1 because logistic regression is a likelihood analysis. So we're trying to figure out the likelihood of either having high blood pressure. And so we're going to need it to be a discrete binary option. It cannot be a continuous variable or a categorical variable with multiple options. If it was continuous, we would need to use linear regression. Some other assumptions: we need a relationship between the independent variables and the dependent variables. Without a relationship, there's no point in doing all of this, so we're going to need to be sure that we have the independent variables are related to the dependent variable. We are going to need to have no or little multicollinearity. Multicollinearity is a perfect relationship between the independent variables, and so we want to avoid having variables that are that have perfect relationships with each other. An example would be, like if you have age as a discrete variable, but then you have is old, is not, that sort of a thing. You want to avoid having perfect relationships where as one goes up, the other one goes up at the exact same rate, all of that sort of stuff. We want to avoid that because we want to avoid false negatives. And when we have perfect relationships between independent variables, it's more likely that we'll have those false negatives because you're pretty much doubling up the power of that variable. And independence, each variable has to be independent of other variables. That's the same sort of story there. We are using Python version 3.10.9 and Jupyter Notebook version 6.5.2. We're using Python because it has strong module and library support. In our situation today for the logistic regression, we're going to need variance inflation factors. We're also going to need from stats models the model itself, the model object for the logistic regression. And so by using Python, we're able to have access to these libraries, which removes a lot of the hassle and a lot of the busy work of the model creation. So that's why we're using Python, and we're using Jupyter Notebook because it has the checkpoint functionality, which allows us to save model state and go back to it at a later time without rerunning the entire model again. So we'll be able to see the summary statistics without rerunning the model every time. For our research question, we are going to need the logistic regression, and the reason for that is the high blood pressure variable is a discrete Boolean variable. It's either a 0 or 1, or a yes or a no right now, but we'll turn it into a 0 or a 1. If we were using a continuous variable or another type of variable, we would need to use linear regression, which we did previously in task 1, but since we're doing a likelihood analysis, we're wanting to use logistic regression. And so that's why we're using it. Next will be the data preparation. So the main goal of the data preparation is to remove all unnecessary data really from the data set. That'll be the main goal of it. We don't need a lot of the survey data. We don't need a lot of the location-based data. And so we can remove that from the data set. That way we just have the variables we need for the logistic regression. So we're going to remove duplicates, we're going to remove missing values, and unused features. First part here is imports, where we got a bunch of standard ones, the math, NumPy, pandas, pyplot, seaborn, all those are pretty standard. We're importing stats models in order to get the logistic regression model, and we're also getting the variance inflation factor in order to evaluate the model. Then we got sklearn here. This is mostly for evaluation. I actually don't think we need that anymore. I was messing around with sklearn's logistic regression one to see if that one would be easier to use, and it was not easier to use. So sklearn is just for evaluation metrics, and also the train test split at the end. That way we can test the accuracy of our model. And import the data right here. Next little section here is we're checking for duplicates and getting the shape of the duplicates. The first one here, the first output number in the set here is the amount of records that are duplicates, and we have 0, so there are no duplicates in the data set. Next thing we're going to do is check for nulls. This is similar to the duplicate check. It just took a little bit more work to get the null values. We sum the null values for each record, and we come back with 0 records with null values, so there are no null values as well. Then we drop all of the features we don't need. As I mentioned before, this is a lot of the survey data here, item 1 through 8, and then a lot of the location-based stuff like city, state, county, zip, latitude, longitude, area, population, that sort of stuff. So remove those there. I have split the summary statistics into 3 portions. We have the dependent variable, which is that high blood pressure. Then we have the continuous independent variables and the categorical qualitative independent variables. I've split it up like this because each of those groups have different methods to be ran against them, and so just run them all at once and get out the summary statistics for each. So first one here, since we have a Boolean value for the high blood pressure, we're getting value counts, so we can see there's about 2,000 more without high blood pressure than there is with, so that's just something to keep in mind when we're doing the logistic regression modeling. When it comes to the continuous variables, we run .describe on all of them. That will get back the count, mean, standard deviation, minimum, maximum, and quartiles for each variable. So we got those here. The only stuff that really sticks out and to keep in mind is that the minimum for age is 18-year-olds, so there's only adults in this data set. And I believe that was the only thing that I had to remember. When it comes to the qualitative independent variables, we are just running the same value counts as the dependent variable on all of these. So we're able to get back the amount of each category for each variable. So for marital status, we got widowed, married, separated, never married, divorced, all that good stuff. I just realized we should probably run this so I can prove that it works. Let me run that quickly. But yeah, those are the summary statistics there. While this goes, okay, we'll let that run. There we go. There we go. All right, so it does work. And next will be the distribution visualizations. For the first section, we got univariate distributions, and we got the high blood pressure here. As you can see back, similar to our value counts summary statistic, we have more no's than yeses when it comes to the high blood pressure. Then we have the univariate visualizations for all of the independent variables. So we got those here. Important things to notice when it comes to marital status, we're evenly distributed. The divorced, married, widowed, never married, and separated are all within a couple hundred values for each, a couple hundred records of each, and that does not match United States averages. I believe, I'll have to double check, but I believe it's married is usually around 50% for the United States, and separated is only around 2%. So we have a much different marital status feature compared to the United States average. So that's something a little different. We also have age is also evenly distributed, and that's a little bit different from the United States average, so that's something to keep in mind as well. And additional charges, it's just important to notice that it has a steep fall off after 15,000. So those are three observations I made when it came to the univariate independent variable visualizations. I do have bivariant distributions, but I did those after the data transformation section, and the reason for that is I was having a rough time trying to get the categorical variables to work with the bivariant distribution visualizations. So I turned them into dummy variables and then was able to do the bivariant distribution visualizations. It was much easier doing that. I hope that's okay, but I'll show you those after this. So when it comes to the data transformation, we are going to convert the data frame object types into categorical for the categorical variables, and we're going to convert the Boolean variables from yeses and nos into zeros and ones, and that will make the modeling much easier. We will also have to do that with the dependent variable, the high blood pressure, and then we will also have to convert the categorical variables into dummy variables. And the purpose of the dummy variables is to split the categorical variables into binary yeses and nos for each category of a variable, if that makes sense. So when you have a gender categorical variable, you have female, male, non-binary. When you split that into dummy variables, you have a male 0 or 1, a binary male or male yes or no. And then from there, you're able to tell if you have a male no, then you know it's the record is either female or non-binary. And by doing that, we're able to feed it into the logistic regression model, and we're able to use it, and it'll be much easier to do so. The other thing that we have to keep in mind is that if you have, in that example, a female, male, and non-binary option, you want to remove one of those because the other two imply implicitly the third one. So if you have a patient who is not male and not female, then you can assume that they're non-binary. So if you have a 0 in the male and a 0 in the female columns in those features, then you know that they are non-binary. If we kept that non-binary feature in the data set, we would begin to have multi-collinearity, which we don't want in our logistic regression model. So that's the what's going on here in the dummy methods and the dummy data transformation. Then we got the bivariant visualizations here, and these ones were, I was a little bit confused by these, but what these show is the distributions of each variable. So we got, going up the y-axis is yes or no if they have high blood pressure, and then across we have either the continuous variable, or discrete variable. So for children, we have, how many, if they have one child, they're here, and as you move along, you have more. So we're able to see the distribution of patients with high blood pressure and without for each variable, the independent variable. The part that took me a while to figure out with these visualizations is if you have them next to, if you have a yellow and another brightly colored option like this green option here, and they're next to each other, that just kind of implies, in this case, that the people who don't have soft drinks are all they're all correlated to each other. So soft drink here being on the lower end, that's just more likely than being on the upper end of soft drink. And it doesn't really factor in the high blood pressure, since they're all kind of on the same side, if that makes sense. And so when it came to these 4 options, the either high blood pressure, no high blood pressure, stroke or no stroke options, it's important that we're looking for just where there's one spot that's yellow colored and then the other ones are purple, for example. We want it to be very distinct, just one option that's very distinct, and that would show us that there's some sort of correlation between the variables. And that was not something I really saw here. The additional charges I did see was spread across the entire range, but there is a bit of a, let's see here, where's the additional charges here? Additional charges is down here. It looks like this one looked a little bit weird, and the reason for that is it looks like the people with high blood pressure are spread evenly across the entire additional charges group, but the people without additional charges are very heavily in the bottom amount of additional charges. And so that was something I saw that was interesting. We will need to do a little bit more research on that. The other thing was a very similar story with total charges, which is here. So the distributions on the lower end seem to be heavily in the no high blood pressure section. So those are 2 groupings that we need to keep an eye on. Next we got is the exported CSV file, and that's a D208_task2_clean CSV. And then on to the actual logistic regression model. Excuse me. There we go. We got the high blood pressure as the y variable and all of the independent variables as the x values. And so we feed that into the stats model, logistic regression model object, and fit the data, and then we get these summary statistics. And so we have 35 variables inside this model as of right now. What we're going to want to do is reduce the amount of variables in that model, and we want to remove ones with high variance inflation factors. That removes ones that are heavily correlated and ones that are skewing the data set. We also want to remove all of the ones that with a very high alpha value, anything over 0.05 we want to remove, since those are not statistically significant for our model. So I got my little VIF removal function here. What this does is it creates a data frame for the variance inflation factors of each variable, and it then finds the one with the highest variance inflation factor. If it's over 10, it removes that factor from the data frame and from the list of variables I have. Then it runs again, and it does that until all of the variance inflation factors over 10 are removed. The reason we have to do this is every time you remove a variance inflation factor, the variance inflation factors change for the other variables. So we can't just remove all of the ones over 10 immediately. We have to continually run this in order to see how they have changed. So that's what we got going on here. It means we remove the total charges, we remove the vitamin D levels, the age, and doc visits from the data set. So those are the 4 that get removed. And then at that point, we have removed all of the variables with variance inflation factors over 10. Then we run the model again. When we run the model again, we're now down to 31 variables. So those are all the ones here. Then we want to remove all of the statistically insignificant variables, all the ones with a p-value over 0.05. And so we take those, we drop all of those from the data set, and we remove those from our list of independent variables. At that point, we have the final model here. For the final model, I did split it into a test and training split. The reason for that is when we get down to the evaluating of the model, it's just way easier to check the accuracy if we already have it split. So I split it 20/80 split, test split, so that's what we got going on here. We feed the training data into the model, and then we fit it, and we come back out with a model with just 4 variables in it. All of the other variables were removed because they were statistically insignificant. So when it comes to comparing the models, I decided to use the pseudo R-squared metric. A pseudo R-squared metric is used because a normal R-squared metric cannot be used on a likelihood analysis. So we're trying to figure out the likelihood of someone having high or low blood pressure, high blood pressure or not having high blood pressure, and you cannot use a R-squared metric for the for evaluating that for a likelihood scenario. And so we have to use a pseudo R-squared, which mimics the R-squared metric. But it's important to note that since with a predictive value like ours, a likelihood value, the error variance is changing constantly. It can't be completely analogous to a R-squared metric. And so we cannot be using a pseudo R-squared metric to compare models that are trained on different data. It doesn't fit the same way as an R-squared metric would. We are able to compare our models that are trained on the same data though, so we are able to compare our initial model to our final model and use the pseudo R-squared metric to compare the two. So, all that being said, that was the first thing I did, was I looked at the initial model, which had a pseudo R-squared value of 1, so that was really good in my head. And then I looked at the last one and saw we had a pseudo R-squared model of 0.38. And so after learning all of that about pseudo R-squared, I saw those and said, uh-oh, something's wrong. And so it took me a little bit of work in order to figure out what was happening. But what it turns out is happening is we have separation, variable separation, which in logistic regression modeling is when one variable can be directly, it has a direct cutoff point where you can see in our case, it would be anything below this point on this independent variable would cause a 0 of high blood pressure, and anything above would be a 1 of high blood pressure. And so one variable is swinging the entire pendulum here. And after some trial and error, what I realized it was this total charge with a VIF value of 826, a very high VIF value. And that one is the one that is swinging everything around and greatly affecting the data. And what it would do is its presence would make the pseudo R squared be 1 constantly. And so that's why the initial model has a pseudo R squared value of 1, while our last couple models were just sitting at around 0.38. And so after all of that about pseudo R squared values, we cannot take this initial model's pseudo R squared value as gospel. We gotta take it with a grain of salt that it has a pseudo R squared value of 1, because the total charges is affecting it greatly. And so we, after the removal of that variable, we're able to compare them a little bit better. And so we're able to see the pseudo R squared value without that total charge in it, the one after all the VIF evaluation is completed and all the VIF values that are too high are removed, including the total charges. We see that one is seen at around 0.39, and then after we remove all the unnecessary variables, we're still sitting at 0.38. So compared to the initial model, it looks like our pseudo R squared value is much lower, but effectively compared to the version without total charges, we're actually very close to the same. And so the short story of the long is don't trust the initial model we had with the 1.0 pseudo R squared value, and the pseudo R squared values cannot be used the same way as an R squared value. Which brings us to the next section, which is, well, if we can't trust the pseudo R squared values, how are we going to evaluate the model? And that will be done through just a simple test and training set. And that is what we do next. So I took the final model we did, which we already fed the training data with, and I ran a prediction using it against the X test variables to get a Y prediction. Then I run a confusion matrix against the test data and the predicted data, and then we get that here. And after running the accuracy score, I also ran precision scores, recall scores, and F1 scores for the predicted data against the test data. And all that being said, we come out with an accuracy of, oh geez, this should be 80%. Should be 80%. I will have to fix that before I turn this in. These are all decimal values. Ignore the percentage sign here. So this is 80% accuracy, precision score of almost 80%, and the rest of the evaluation metrics there as well. So we're sitting at about 80% accuracy for the model that we created, which is awesome. The next section is the executable code. I'm not sure if we need to turn in the above code snippets as the executable code, or if we need a separate Python file. So I did create a separate Python file, which is available with the submission. And to run the file, the only caveats are you're going to need NumPy, Pandas, Matplotlib, Seaborn, and Stats Model libraries in order to run it. So those either have to be in the environment already or on your computer. Just something to keep in mind before running that. So now on to the data summary and implications. So we got the equation here, which includes all the variables that are within the model. And the practical interpretation of the equation is a patient's chances of having high blood pressure can be interpreted as all things being constant. For each extra dollar in additional charges, the patient will have an additional 0.03% likelihood of having high blood pressure. Then if the patient has a stroke, the patient will be 15.26% more likely to have high blood pressure. If the patient is overweight, the patient will be 14% more likely to have high blood pressure. And if the patient has a medium complication risk, the patient has a 14.88% higher likelihood of having high blood pressure. So that is the practical interpretation. I believe, based off of everything we've done today, the model does have practical and statistical significance, but we need to the practicality of it, while it's 80% accurate and we are able to see exact percentage chances of an increase in high blood pressure, some of this stuff is a little harder to interpret, I guess is how I would phrase it. Like the example I would use is additional charges. We can use that in order to increase, for every extra dollar in additional charges, increase by 0.03% the chances of having high blood pressure. But in my head, you wouldn't really have the additional charges amount until after a patient has been admitted into the hospital system, in which case you would hope they already have the high blood pressure value. So the additional charges value, while it's important for this model, I'm not sure if practically that's something we're able to have access to before we need the high blood pressure amount. I also think something like medium complication risk can be heavily subjective, and so that's something to keep in mind as well. And the final thing when it comes to the significance is, while 80% is of high accuracy, statistically significant accuracy, I do question if that's enough for people to be making health-related assumptions and also financial assumptions. And so those are my only problems with the practical significance of the model. And if we some limitations of the model, when it comes to high blood pressure, in my head, I think it would be better to have a continuous variable for that value, and that would make it so we couldn't have a logistic regression model. But I feel like having a continuous variable for that feature would provide us with a more accurate and more precise way of measuring, and perhaps using a linear regression model instead, and it might provide more insight into patient health if we have that. And similar problem with overweight. Being overweight isn't necessarily the only problem that you can have when it comes to weight-related features. A underweight value can be just as big of a problem as an overweight value. And so perhaps using a categorical feature or continuous BMI value would provide more insight when it comes to this feature. So that's something to keep in mind as well when it comes to limitations of this model. And at this time, I mentioned all the issues with the practical significance that I had. I'm not completely comfortable with recommending a course of action with this model. Perhaps if we're able to increase the accuracy a bit more, get it maybe up to like 90%, I would feel more comfortable making assumptions about people's health and finances, stuff like that. And if we were able to figure out how to use additional charges and medium complication risk and remove those issues I had with the practical significance, perhaps then we would be able to make a strong recommendation to use this in a practical setting. But until then, I am not comfortable with making any recommendation using this model. And that is my logistic regression modeling performance assessment. I appreciate you checking it out and hope you have a good one.